So we're going to be looking at acid-base buffer systems. And these are going to be a solution that contains a conjugate partner for both an acid and a base. So we're going to have the pair of them in there. And they can't just be just any acid-base conjugate partners. They have to be a conjugate pair where both of them are weak. Theoretically, they don't have to be conjugate partners. You could just have a weak acid and a weak base. It could work, but they have to have more than one buffer system. So we're going to stick to relatively simple buffer systems with this one. So we need a pair that is conjugate partners of each other, and therefore one's the acid, one is the base, and this allows them to establish an equilibrium where you can have some amount of each one of them. If one of them was really strong, then you wouldn't have very much of that, so it would not make a very good buffer. We want to have some amount of both the acid and the base, and if they're conjugate partners, then when they do their thing, the acid being an acid or the base being a base, they would then just form their conjugate partner. Essentially, we are going to use ones that are the same concentration, but we want a decent amount of each one. So we'll say, okay, let's start with the same amount of the conjugate acid and the same amount of the conjugate base. And then this will allow them to resist a certain change in pH. It doesn't eliminate a change in pH, it just buffers the change in the pH. So with the two partners in there, the base can take care of any hydrogen ions that show up, and the acid can take care of any hydroxide ions that would show up, and they can be neutralized then, leaving behind the conjugate partner. So if the base takes these hydrogen ions, then it would turn into the acid, the conjugate acid. If the acid uses its hydrogens to neutralize the hydroxide, then whatever acid does that would have lost its hydrogen and it would turn into its conjugate base partner. So we'll see how that works. This will lessen the pH change. So even if you eliminate the hydrogens or hydroxides being added, you're still going to get some pH change because you're going to be forming some amount of the conjugate partner, which is going to have an effect on the pH, but minimal compared to what it would have been if the hydrogen or hydroxide were not neutralized. So for these ones, often these buffer systems happen, I think of it like in a container of food or something like that. So if you have a can with a bunch of food inside, everything is already in there. And if, say, over time the food starts to break apart or break down, it could be releasing hydrogens or maybe hydroxides, and so that would change the pH of the solution. So what they do is they have a buffer in there as well, and that would minimize the change in the pH and hopefully keep the food as is. Or in like a biological system like yourself, your volume doesn't change when you exercise, but what could happen is you're producing more carbon dioxide, so you'd be increasing the hydrogen ions in your blood through the production of carbonic acid from the carbon dioxide, and we're dealing with your volume not changing. Everything that is there is already there. We're just changing the conditions acidic wise in terms of hydrogen ions or hydroxide ions. So for these types of questions, we're going to mimic that, and we're going to assume that there is no change in volume, also making these relatively easy questions to solve. So for example, if you had acetic acid and acetate as your buffer system, you'd want to have some amount of acetic acid, some amount of acetate, and obviously the acetic acid is going to act as an acid. The acetate is its conjugate partner, and so if the conjugate partner were to pick up hydrogens, it would become acetic acid. If the acetic acid had to donate some hydrogens to maybe neutralize hydroxide, then it would become its conjugate partner, acetate. So these would make a good buffer system. The acetate could take care of any hydrogens that showed up. The acetic acid could take care of any hydroxides that show up, and when they do that, they become their conjugate partner. And so we only have one equilibrium system to worry about. Once these have been neutralized, and in this case, acid becomes its conjugate partner, or if hydrogens were added and had to be neutralized, the base, acetate, would become its conjugate partner. Then we'd have some new amounts, and we'd have to calculate what the pH would be based on that. So let's try this out, starting off with just the pH of the buffer system before we do any changes to it, before we add any hydrogens or hydroxides to it. And again, we've got ammonia and ammonium as our example buffer system, conjugate partners of each other. We have a decent amount of each one, meaning that they'll have a certain amount of either the base or the acid to act on either a hydrogen ion or a hydroxide ion, whoever needed to be neutralized. So to start off with this, we should recognize that we can skip a couple of steps now that we've been doing acid-base equilibriums for a while. So this 100 rule that we've been using to say, do we really need to solve for x, or do we need to run through the quadratic, or can we just skip it? Because we're starting with a decent amount of these things, and these things are weak, for both of those rules, X is going to be really small. So because they're weak, the Kb of the base, or the Ka of the acid, is probably going to be pretty small. And because it's a buffer, we're probably going to be dealing with a decent amount of each one. Otherwise, it wouldn't make a very good buffer because it would be exhausted very quickly. It would run out of the stuff really quickly. So we tend to start with a decent amount of them. For both of those reasons, if we think about our ice table and our changes, the change is going to be pretty small. We still want to find out what it is, but relative to the initial concentrations, it's probably going to be insignificant. We can check with the 100 rule. But again, looking at the K, you could probably ballpark whether the 100 rule is going to work out or not. If you want, you could always set up your ice table and you could check the 100 rule. But what we're seeing with these ones over and over and over again is that large amounts of the stuff, small K values for the entities within it, essentially means we can jump right to the equilibrium expression. So imagine we had our buffer system. We have our acid on one side, we have our base on the other side, and this is imagining the acid dissociating from left to right to become the base, or if we wanted to, we could think of it coming from the right to the left. Either way, right now I'm considering the ammonium acting on water, and then I'd be solving for the pH that would result from that. So I'd be using the Ka of the ammonium, and I can again jump right to my equilibrium expression and say, okay, I've got my amounts. My ammonia originally was 0.23, my ammonium also 0.23. So again, you could probably skip this step and say, okay, if they're in equal amounts, then they're just going to cancel out. So the concentration of the hydronium or hydrogen ions is going to be equal to the Ka value for this acid as I have set it up. Makes it easy to solve. That's the concentration of the hydrogen ion or hydronium ion to be correct. Negative log that, and you've got your pH. Now, it's a buffer system. We don't just have this ammonium. We also have ammonia. So you might be thinking, okay, well, what if we consider what this ammonia is doing? And we do have it in our equilibrium expression, but maybe wanted to consider it acting on water instead of the ammonium. So if we wanted to, we'd say, okay, let's look at it from the base's perspective. The base, we could think of it as acting on water, in which case we've got our ammonium, and it would be producing hydroxide in that case. So using the Ka, we can use, again, these are conjugate partners, so we're allowed to do this and solve for our Kb. So the Kb of the ammonia moving from left to right in this particular equation, producing hydroxides, would be 1.785 times 10 to the negative 5. Again, really small K values, decent amounts of initial concentrations. So we can assume X. I'm skipping right over the ice table, and I'm not showing the 100 rule, but essentially we're doing that in our head at this point. So again, because those concentrations are equal, they're going to cancel out. So this Kb here of the ammonia is equal to the OH concentration. So therefore we have 1.785 times 10 to the negative 5 moles per liter of OH. We negative log that. That would give us our POH. And if we convert that to pH, we get the exact same answer. So it doesn't matter. Don't do both. Pick one of them and look at it from that perspective. Choose the acid. You got one less step. And again, we're skipping the ice table. We're skipping the 100 rule, or essentially doing that part in our head and jumping right to the equilibrium expression, which is even easy to do from there because we just have equal concentrations. So a lot of steps can be skipped in the buffer questions if we're making these assumptions correctly. Part B would involve looking at, okay, we've got this system and we've got the pH that we just solved for. What if we then tested its ability to be a buffer by adding some hydrogen ions in this case, or we could do hydroxide ions, but this one is adding 0.1 moles of a strong acid. And we're going to deal with a 1 liter solution. And again, we're going to assume there is no change in volume, which is often the case with a buffered solution that's already got all this stuff there. It's just there happens to be a particular change that causes some hydrogen ions to be released, in this case 0.1 moles. So if it's a strong acid and we've got 0.1 moles, we can assume this, we know it's in 1 liter, so we know that the hydrogen ion is 0.1 moles per liter in concentration. And this again, being in 1 liter, we know it's 0.1 here, that's its concentration. We could say, okay, without the buffer, we could just find the pH of 0.1 moles per liter of hydrogen ions, and that would give us an incredibly low pH. But thankfully, this is in a buffer system. So being as this is hydrogen ions, it's going to be the base whose job on the buffer is to pick up hydrogen ions, and in doing so, it would be forming its conjugate partner, ammonia, therefore neutralizing the acid, the hydrogen ions, but it would also neutralize a certain amount. Remember, we have 0.23 moles, assuming we have 1 liter of the stuff, 0.23 moles of this ammonia, so we could neutralize up to 0.23 moles of the hydrogen ions. We're only using 0.1 moles of it because there's only 0.1 moles of the hydrogen ions, so we can do the math on that and say, okay, well, of the 0.23 that we had, we're going to use up 0.1, and therefore there's going to be 0.13 moles of ammonia. So the new equilibrium concentration, and again, assuming X is going to be small in the equilibrium adjustment, our concentration, and this would be the initial ammonia concentration, but because we're assuming we can ignore X, we're going to use that as our equilibrium value as well. But we need to realize that as this 0.13 moles of ammonia gets used, we are going to end up producing an extra 0.13 moles of the ammonium. So this ammonium, because it is the conjugate partner of the ammonia, as the ammonia picks up these hydrogen ions, it becomes this ammonium. So it would have gone from 0.23 up by the 0.1, because 0.23 moles of, or sorry, 0.1 moles of the ammonia became the ammonium. So now we have an equilibrium concentration of the ammonium at 0.33, the original 2,3 that were there, plus the 0.1 that was created in the neutralization of the hydrogen ions. With this, we can then, again, we're assuming X is small, we can put this into equilibrium expression. We have a nice easy volume to work with here, so the moles are in 1 liter, so that's going to give us a direct moles to liter conversion. You could set this up in a nice table. Again, small K's, big initial concentrations, even though we're down to 0.1, still pretty big relative to our K value. So we have our new concentration of ammonia, which is less than it used to be because some of it was used to neutralize those hydrogen ions, and our ammonium concentration, which is now 0.1 higher than it used to be because it was formed when the ammonia became the ammonium. And so now, using the Ka that we used before for our ammonium, 5.6 times 10 to the negative 6, we have our new concentrations at equilibrium. Again, we've done the ice table in our head, we've ignored X, so we're good with that. And then now we can solve for our hydronium ion concentration and negative log that, and we get our new pH. So we did see a change in pH due to the hydrogen, but it is not nearly as much of a change as we would have had the solution not been buffered. So it has become more acidic, but not nearly as acidic as if you just had that 0.1 moles per liter of hydrogen ions, moles per liter of hydrogen ions. That would give us a very acidic solution. With this buffer and having the ammonia sort of sacrifice itself to scoop up these hydrogen ions, we are going to be able to maintain a relatively constant, though still more acidic, just not very much more acidic, pH of the buffered solution.